So buffers are acid-base systems that resist changes in pH. That means you can add a strong acid or strong base, and the overall pH will change just a tiny bit compared to an unbuffered system. But let's talk about how they work. So in a buffer, you actually have a weak system. Remember, weak acids and weak bases don't come apart fully in water. In fact, they stay together almost entirely. So weak system. And the difference between a buffer and not a buffer is that you have both your acid, which is your HA, and its conjugate base, A-, present in the same solution. It's best if they're in near equal concentrations. That allows the buffer to work in the best way. So let's talk about how a buffer works. How does it resist pH change? So if I have HA and A- in near equal concentrations, and remember, they're at equilibrium. So I have a dynamic conversion of HA to A- and A- back to HA at equal rates. That means that if I perturb the system, equilibrium will try to reestablish. So let's talk about perturbing, right? What happens when you mess with a buffer is you add a strong acid or strong base. So if I were to take my system, which contains HA and A-, right now, they're at equilibrium. You can imagine a teeter-totter where I have my acid and my base balanced. But then let's add a strong acid to this system. Strong acids come apart completely. So that strong acid is going to make a lot of hydronium. That's H3O+. Is that going to react with anything? Yes. It will, because you have a base in your system. It's not a great base, it's weak, but it will definitely react with that strong acid. So that strong acid is H3O+. It's going to react with A- and shift your equilibrium and make more HA. So if you add a strong acid, you've just tilted your teeter-totter. Now you have more HA than A-. You've also ended up consuming some of that hydronium that was the strong acid. Now what's going to happen? Well, now the system, it's gone out of whack. You have a different concentration of acid and base. It will reestablish equilibrium and come back into balance. That's buffering. If I didn't have the buffer there, I wouldn't have any A- or conjugate base to react with that acid. That acid would go right to changing my pH. But because I have something present that can consume it, and my product is HA and A-, then I can re-equilibrate, and I end up seeing a very slight change in pH. Likewise, let's talk about when we add a strong base. If I add OH-, what's it going to react with? The best acid it can find. And the best acid in our system is our nice weak acid HA. So the strong base is going to react with HA, it gets consumed, but then what does it make? It makes more A-. So if I add a strong base, what did I do? Now I've shifted my ratio of A- and HA, where I've made more A-. Then this system is out of whack and it will start to re-equilibrate as well. And so my buffer can keep resisting that pH change by sacrificing part of itself, consuming part of the conjugate base or conjugate acid to make the other, and then re-equilibrate. This is why buffer calculations always involve two steps. The first step is to figure out how out of balance your teeter-totter is. So you need to decide whether or not you have an imbalance of HA and A- and how much of each. Once you know those concentrations, then you can calculate the new pH of your buffer as it re-equilibrates. That would be the Henderson-Hasselbalch equation, which you may have heard of. Why do we care about buffers? Well, actually, buffers keep us alive. We all have a buffer inside of us right now. Your blood is buffered very carefully with a carbonate system to make sure that the pH of your blood doesn't change that much, even when you are doing crazy things that produce lots of acid, like running, for example, and you make lots of lactic acid, you have to somehow balance the pH of your blood so it doesn't get too acidic. So thank goodness for buffers that keep all of us alive. Hey, we're gonna make more of these videos, so let me know what you want to hear about in the comments below.